Let's look at some code that will do golden section search inside Steepest descent and bracketing before we do the golden section search. So it's all the usual stuff here. We're defining an objective function that's just a plain quadratic, 0.3x squared plus 5y squared. We could make a more interesting quadratic, and we'll do that in the next lesson. Here we're setting it up to record the x values and the function value every time it gets called, and that will help us do some plots later and see what happened during the evaluation. There's also this function we haven't talked about yet called the Rosenbrock function that has an interesting little twist to it in trying to optimize. So some people use it as a kind of test function when they're writing nonlinear programming solvers. And then here's our bracketing method. We give it a function and tell it an initial alpha size to step forward, and if we don't tell it 1, it will just default to 1.0. I have a little code here because I was getting bad results, and so I said, okay, let's actually evaluate the function at a bunch of different x values, but now I don't need that anymore because I got it fixed, so I commented it out. So we're just saying, did I find a bracket on the first try? If so, just send it back and quit. Otherwise, make the outer edge of the bracket bigger by a factor of 2 each time until we know that we've captured the minimum because our objective function went up again. That's what we're doing here. And it's good to write little tests for each individual function so you can be fairly sure it's working before you go on and use that function in another function. So that's what we're doing here, just trying to find a bracket for x minus 10 squared. So you know the minimum there is at 10. If you start at 1, it should go 1, 2, 4, 8, 16, and so 16 is the end of the bracket, and it realizes that 4 was a better start of the bracket than 2 or 1 or 0, so it gives that back. Alright, so we've got bracketing set up. Here's golden section. You give it the one-dimensional function you want, you give it the bracket you just got from the bracketing, and what kind of tolerance, how tight you want that final interval to be. Here it's relative, so you could say basically 1%. You don't have to change that if you change the units of the x values or something. Here we're defining the two big constants that the golden section search uses, 1 over the golden ratio, and then the complement of that, 1 minus that. We're going to keep our 4 points in this order. We're just saying if the function here is less than the function here, then go left, otherwise go right. And what we're saying is we're copying the function value here and here, and then evaluating the new function value at 1 point. That's the whole point of golden section, is that you can reuse some of these others rather than evaluating them again. All right, and then here's a little test function for that. In theory, golden section doesn't depend on having any derivatives. It should even work for a function with flat spots or even discontinuous functions. So that's what we're testing here. It's kind of fun. And then in steepest descent, instead of depending on someone writing a function to compute the gradient for any particular objective function, we'll just use finite difference. So this is just in sequence changing each element of the vector by a little tiny bit, which defaults to 10 to the minus 5. When I write for loops now, I could just say for j in something, but then if you're searching for the index, if you search inside a page for the just letter j, you'll probably find a bunch of stuff. But nothing really uses double j, so that makes it easier to search for occurrences of where you're using that. The same thing with I occurs a lot of the time, but double I doesn't. So here's our steepest descent with embedded golden section search. You send it the multidimensional function you want to optimize. You send it your initial guesses, some options like how much tolerance do you want in the line set searches. Do you want to display individual steps or not? And how many steps you want to take. So this is a very simple approach to when should I stop. We're just going to tell it do 10 steps. If we wanted to be fancier, we could implement, is the gradient small enough kind of rules. Setting up some place to store all the steps we take. and then just finding the derivative, recording that, doing a line search, or doing the find a bracket, then the line search. If we told it to display things as it went along, it'll do that here. And then actually use the line search value times the negative gradient. That's our new step. And then once it's done with all those iterations, we're just saying in however many steps we were told to do. And then give back all the history of the stuff we tried. So now we're ready to run it. So we set up some options, we tell it where to start, make some room for history stuff to be recorded. We could just say steepest descent and then give the name of the objective function we want, like quadratic, but we want to evaluate the objective function later when we're doing contours and stuff, and I don't want to have to go change that name for the function when I change this name. So here I can just have a name that points to this function and then use that name later, and then if I choose a different function, then I can just keep using the word objfun, and it will keep working. So we're actually telling it to do the optimization here, sending it what function to work on, the initial values, what our options are, and how many steps. And then saving a copy of stuff and doing a little report. I already executed this. This was from the bracketing, I think. So it only had to expand the bracket forward a few times, 3 times out of 10 major iterations. Here's the history of every time it evaluated the objective function. You can see it started here. Apparently, then when we asked for the gradient, it evaluated it again. We could have been more careful and said, here's the function value I already know, but that would kind of obscure the flow of the code. And then you can see here the first x value is changed by just a little bit, so that's a finite difference step. And then here the second coefficient in the vector is changed by just a little bit. That's the other part of the finite difference. And then we go back and start doing bracketing, and then it's hard to spot what's bracketing in line search here, but at least we saw the initial finite differencing to find the gradient. We said the other day that if you do an exact line search, then the new gradient should be perpendicular to the old gradient. And so computing the angle between successive steps might be interesting because you're kind of thinking it'll be 90 degrees. But for a line search, the angle between successive steps should be 0 because you're just going forward, or sometimes you come backwards, so then it would be 180. So that helps us identify what's going on. So just ordinary kind of trig stuff there. And now we actually start plotting what happened. First we decide what X and Y window to use, and then our usual code that evaluates objective functions. So this is what our objective function looks like in 3D. Here it is as a heat map. Here's the contours and the trace of every point that it tested. It started here and then went there, and after the line search found that and then went over this way, and I'll show an animation of that in a sec. Here's just the trace of where it went, but not forced to a 1-to-1 aspect ratio. So this angle doesn't look like 90 degrees, even though mathematically it might be 90 degrees. And then we plot just the major iterations, so the times when it computed a new gradient without all the line search stuff. And here it's kind of hard to see, but here's a zoom in on it, and that does look reasonably 90 degrees-ish. And we're seeing that kind of zigzag behavior. Here it is again on the contour plot, and then here's an animation. I already ran it. It takes a while to run, but let's show the animation here. Maybe we'll zoom out a bit. And it says ls when it's doing a line search step, and it does a red dot to show what the most recent point is when it's not doing a line search. So that might be finite difference or bracketing, or the first bracketing step. And right now it doesn't look like it's moving very much because it isn't. It's already so close to the minimum its steps are pretty small. So the last like 10 seconds of this animation, which is 100 frames, it's refining that optimal position and not spending much time searching around. All right, so animations are fun. If a picture is worth 1,000 words, someone once said that an animation is worth 1,000 pictures. All right, so then we can say, how did the objective function value change as we went along? Can't see very much in this plot because it found pretty good solutions pretty quickly. But if we do it in a semi-log y scale, if we see linear decrease on that, then that would mean the objective function value is falling off exponentially. This isn't smooth. Can you figure out why we're seeing what we're seeing here? I should point out that this is the x-axis now is how many calls we've done to the objective function, so that's kind of like time. And this is the log of the objective function value minus its optimal value. So these flat spots, it's probably trying finite differences, so we're not seeing much change in the objective function. And then it tries bracketing, so it goes pretty far away, so that makes the objective function value worse. Then it kind of comes back, and then does maybe some more of the line search. We can also look at the ratio of one objective function value to the next, because if it's exponential decay, then that ratio should be roughly constant. But with all that line search stuff going on, we're not seeing that. If we look just at the major iterations, maybe that would be the case. And then if we look at the angle from one to the next in degrees, we're seeing lots of zeros, that's a forward part of the line search, lots of 180s, that's stepping backward, and then some 90s, one there, one there, one there, and those are probably the major iterations where it's saying, okay, let's get a new gradient. And that's it.